In this video, we're going to review some of the other properties caused by intermolecular forces among liquids. To start with, a common one for liquids is the surface tension. This is what holds the liquid together to give those little domes of droplets, while your water, when it hits the table, will beat up into little balls and form raindrops. Surface tension is what pulls the liquid together. Well, if we think about it for a minute, if I've got a big bulk here and I got water all the way to the top, there's water molecules on the inside and there's water molecules at the surface. Now, any molecule on the inside is going to have attractive forces from all directions to other water molecules. This gives the most possible interactions. There's a bunch in all directions. But any water molecule at the surface is more limited. It'll have some interactions, but those interactions effectively only are half the possible directions. The top half is just missing compared to the molecules on the inside of the material. This means there are less interactions on the surface. This is not as desirable a state. If you've got a large bit of water on a table and it's spread out wide, then you have many water molecules that are at the surface and some that are on the inside. Well, by random motion, these will bounce around, and any that move further in develop more attractions. This makes it harder for them to move back. That means the edge of your water starts to move in, and slowly what'll happen is you'll get a little bit more of a dome and a little bit more of a dome as more and more of your particles move away from the surface and get onto the inside. Now there's a limit to this. Eventually you've tightened up as much as you can and reduced your surface the maximum amount. A free-falling drop ideally would be round. Your sphere has the least surface area for the same volume. Remember that your liquid always has the same volume, no matter what shape you stretch it and twist it to. There's only so much stuff, and they're all held together at the same force and so at the same density. And so your volume can remain constant while your surface area can change as you change the shape. The shape with the least surface area is the sphere. Well, surface tension involves those attractive forces. They're holding things together in various directions. They're trying to pull together. Eventually, you get your material as pulled together as it can get. Well, there's still molecules at the surface. They would love to be further inside, but most importantly, the ones inside don't want to be back at the surface. But if you were to cut a droplet, suddenly you create new surface. Molecules that used to have interactions no longer do. The net result is that energy had to go in to separate those water molecules from their attractive forces with each other. It takes some energy to break that attraction, and that is what we think of as the surface tension. When this is at the surface of your material, effectively to push through, you're going to have to expose internal molecules and break some of their bonds to each other. This is why sticking an ore into water can take a little bit of work. You have to part a whole bunch of water, separating it as it slides across the ore. Those water molecules on either side used to be connected to each other. The stronger the attractive forces between molecules, the more difficult it is to actually break these bonds. To the point that if you try to row in, say, mercury, imagine that you had an iron boat floating in a pool of mercury. Attempting to stick an ore into mercury is very difficult. It's almost like slamming it into concrete. It resists because there's an immense attractive force between those mercury atoms. Easily 10 times or more that between the water. This property of being attracted to the bulk material surrounding the liquid versus the surface plays out in some of our other properties, such as capillary action. If you had a container of liquid and you were to have a glass tube and you insert that glass tube into the liquid, you may notice that the liquid will flow up it a little ways. And if you had a narrower glass tube and you were to dip it into that liquid, you notice that the liquid would flow up further. You may have seen this with a straw. It'll go a little ways up the straw, but if you ever had a chance to do it with this narrow glass tube, you can get liquid to travel quite a ways up it. So what's going on here? Well, if we think about the surface of that glass, it's silicon and oxygens and O minuses from the silicates. And so it makes up a lattice of silicon and oxygen. Well, water can be attracted to that. Hey, water's got those hydrogens. They're fairly positive, so they're going to be attracted. And all the other water molecules are still adhered to one another, but they can adhere to that glass. That O minus is charged, and so it's really good at interacting. Dipole ionic attractions are very strong. As a result, any water molecule that kind of drifts up to the next one, rolls over, it can be attracted to the next one up the line, and so your water can kind of climb the glass. However, there's water in the middle between the walls. This is not one molecule across. And so there's still water molecules adhered to the other water molecules. They're sort of weighing it down. Imagine you had two ladders and you had a climber on each one. And you had a rope between them. If there's nothing on that rope, these climbers can probably climb all the way up. Big deal. However, if you had some weights dangling, and as the climbers climbed up, they'd reach the end of the length of rope. Those weights, a few of them would go taut. Others would still be hanging at the bottom. They'd have a longer rope and still be down. There wouldn't be as much weight pulled up yet. But as these kept going up and up, they'd be forced to carry more and more of that weight that reached the end of its rope and now was just being drug up. And so as these two people would travel further up their ladders, an ever-increasing amount of weight would be carried with them. Now, eventually, this would be too much, and they just couldn't go any higher. The pull of the weight pulling them back down is overcoming their muscle strength to keep going higher. This is effectively what's happening in glass tubes. There's a volume of water, which means there's a weight of water in that tube. That weight is pulling all that water back down into the bulk below, and it's opposed by the attractive forces pulling glass and water together on the walls. When you start at the very bottom, well, there's very little total mass, and so those molecules can climb the wall pretty well, but the further up they get, the larger the mass they're dragging with them becomes. A narrower tube means that you have to go higher before your volume's the same. In these two tubes, if we were to look, our volumes will be, well, there's a little bit of a calculation for it, but they tend to be fairly proportional. The attractive force that the molecules can climb with is opposed by the weight of the water that they're dragging with them. And so eventually it reaches a maximum height. Actually, calculate out the surface tension using this. If you were to have a dropper and you had a bunch of liquid in it, and you start to let a drop form, it'll grow a little, grow a little, grow a little, and eventually gets big enough that it breaks free and falls. Well, if you can weigh that, that weight is going to be equal to 2 pi r times the surface tension. This is a little bit of reverse here, but we can do this similar calculation with capillary action. You can actually figure out the surface tension due to how strongly things will adhere to the thing containing them. This is another property that emerges from the intermolecular forces in a liquid. As that liquid interacts with the walls of a tube, it can start to climb them, but it will also drag the liquid with it. And that leads to an opposing force, an attractive force pulling your liquid up along the walls, and gravity pulling them back down through the bulk material being carried in the middle of the tube. On top of it, for liquids, we discuss things like viscosity. Viscosity is a measure of how easily the liquid flows. Imagine syrup versus just regular water. Syrup pours, but it's slower. It drags on itself. Basically, molecules need to move over themselves. If you've got a container and things start to pour out of it, As they start to roll over, well, the individual molecules have to move to do it. They're up here all in place, and they've got to start moving to start falling. That means the molecules have to roll over each other, which liquids can do, but every time one of them moves out of place with another, it has to break its attractive forces. So there's attractive forces all over, and they're free to kind of rearrange as this one moves and eventually gets over here and makes more attractive forces after having broken some earlier, but others came in to take its place as they all flowed. But for a moment, while it's moving, it has to break some to go on and make some more. That takes some energy. It takes time for that molecule to accidentally have that energy. As things are trying to move, they're dragging on one another. The stronger the attractive forces holding them together, the longer it takes for them to overcome it to successfully move as they keep flowing. So something with a high viscosity flows very slowly because it has strong intermolecular attractions. Something with a low viscosity tends to flow very easily because it has weaker molecular interactions. So while water has some fairly good molecular interactions, syrup and the like has a lot of sugar in water, and there's an enormous amount of interactions between sugars and each other and sugars in water. Each glucose on sugar has 6 different OHs that can hydrogen bond to waters and to other sugars, and breaking all of them, or at least enough of them to get the molecule to move past another molecule, can be very difficult. A lot of times larger molecules tend to have a higher viscosity as they drag along each other more. Specifically, since we live on Earth and we're a life form, we also care about the special properties of water. Water is just unique among liquids that are readily available. It tends to have a very high specific heat, meaning that it takes a great deal of energy to heat it up, but it also has to give away a great deal of energy to cool down, which means it doesn't change temp very easily compared to other materials. This is good for a life form. If it suddenly gets cold quickly outside, or you're running through the snow somewhere, you don't instantly freeze. It takes a lot of time to lose that much heat to really cool down water. Same going out into the sun on a hot day. It takes a while for you to really heat up. Additionally, it's very polar, and yet still liquid. It's got more or less a negative side and a positive side. It can interact very strongly with ionic materials, but it's still small enough that it tends to roll freely around itself, passing on to other molecules. And so it is reasonably easy to be a liquid despite being very polar by its nature. This gives it amazing solubility properties. It's good at solubilizing ionic materials, as well as small polar molecules and small gases. Because it has reasonably strong permanent dipole, it tends to interact with gas molecules, which tend to be more neutral, and induce dipoles in them. The structure of water also tends to encapsulate things fairly well. As water interacts with other water to make kind of little grids and spheres, it's able to surround and solvate things very well. As a result, it can pull lots of ions into solution, it can hold a good amount of gas, and as a result, it's just generally a very good solvent for many different things. Other than very non-polar materials, like oils, water tends to solubilize things very well. The other major interesting part about water is that its phase diagram, when we think about it, is a bit off from most. You have your gas, you have your liquid, you have your solid. It has a negative slope for the solid-liquid line, which means as your pressure goes up, you actually prefer being liquid. The most dense state of water is liquid at about 4 degrees Celsius. This has all sorts of interesting properties in how it affects the world around us. Most notably, ice forms on top of water because the ice is less dense than the water. And so we tend to get a sheet of ice on the surface of lakes and things instead of freezing from the bottom up. As a result, well, a lot of the heat transfer is lost to the atmosphere, And solid ice is actually reasonably insulating. And so once this top of a lake begins to freeze, it insulates against losing that thermal energy to the atmosphere from the rest of the lake. So organisms living below the surface tend to survive because they are not frozen solid. Additionally, as water becomes 4 degrees Celsius near the surface, it tends to sink. This will push water from further down up, cycling nutrients off the bottom as it kind of swirls the material back to the surface. That lower water that was less dense will then cool and then sink itself. And this will churn the material from higher layers and lower layers in an aqueous environment. This also brings gases from the surface down to lower levels, and there's a lot of changes in the environment caused by this cycling with water. And so look at some of the other liquid properties as well as the special considerations for water that come from the intermolecular interactions of our molecules.